Hi, Leo students. Mr. Kaczynski with you again, and we're going to go over thinking with mathematical models, problem 4.3, correlation coefficients and outliers today. All right, so we're going to talk about what those things mean. So this graph below, you got your note sheets. You should be kind of writing down everything I write, maybe some of what I say too, so you can remember it and have it in your notebooks for future reference. All right, so here we go. The graph below has a correlation coefficient of 1.0. All right, so what do we think that a correlation coefficient of 1.0 means? Correlation coefficient. So take a look at that, and what do we notice? Okay, so the correlation coefficient really has nothing to do with slope. It's just about relationship. Okay, how strong is the relationship? So let's write this down. A correlation coefficient of 1.0 is a, how about we say, perfect relationship between, I spelled efficient wrong. I did. I forgot an I. What there? The independent variable and the dependent variable. This is shown by a straight line on the scatter plot. Okay, so it's really just about there being a perfect relationship, a straight line. The slope doesn't matter. It can be a steep slope. It can be a flat slope. It can be down. Well, actually, it can't be down. We'll get to that in a second. Okay. So here's what I want you to do. I want you to pause the video, and I want you to just kind of take a quick shot at this. Match which of these 6 scatter plots has a correlation of -1. So which one has a correlation coefficient of -1? And then I also want you to match these correlation coefficients with the other 5 scatter plots. And we use correlation coefficient, we use R. So we'll get to that later. Just match these 5 and -1 with each of one of these graphs. So just pause the video and take a shot at that, and then I'll tell you the actual answers. Okay, I'm going to assume you're done now and you've unpaused the video. Here's what we got. So the correlation coefficient of -1 would be this one right here. And we use R, so I'm going to write R equals -1. And that is a perfectly straight line right there. Okay, so it's a perfect negative correlation. So as X increases, Y decreases by the same amount every single time. And maybe we should write that in here on a definition of positive one. A correlation, the perfect positive relationship between the independent variable and the dependent variable. Okay, so this one's a perfect negative correlation. So let's look at some of the other ones. Okay, maybe we jump to the other one that's so clear here, and that is F. This is R equals 0.0. Because there's no correlation, right? Maybe we should write that down. No correlation. We kind of saw this yesterday with the GPAs of students at different ages at Magnolia High School in the last lesson. So no correlation there, okay? So anything in between would be these other numbers, 0.4, 0.8, -0.4, -0.8. So let's look at this. I mean, this one's pretty close to a line, right? But not perfect. So that's why that is R equals 0.8. Close to +1, but not perfect, okay? And likewise, this one, again, pretty close to a line. That's why this one is R equals negative 0.8. Close to a perfect negative correlation, but not absolutely perfect. Okay, again, this one, I see a line, but it's not as strong. It's not as strong. The points aren't as close to the line in A as they are in C. So that's why this is much weaker, and we call this a correlation coefficient of about 0.4. This one, similarly, oh, that's not a very good line, goes down. The points are not grouped as close to that line as they are in E. So this is a correlation coefficient of negative 0.4. Okay, so we'll look at these more kind of as we go. Obviously, the grouping of the points and their closeness to the line depends on the scaling of the graph too. And that's something that's not indicated on these graphs, but this kind of gets the idea going a little bit. All right, let's talk a little bit more about this here. All right, the scatter plot below, I'm going to go dual screen here. The scatter plot below shows the relationship between the top speed of a roller coaster and its maximum drop. The pink dots, which you can't see on your note sheet because I did black and white copies, the pink dots represent wood frame coasters and the blue dots represent steel frame coasters. Okay, suppose you drew one linear model for the data in the graph. Could you use the model to make an accurate prediction about the top speed of the roller coaster with a given maximum drop? So if I were to put a line on here, and let's do that, I'll use, oh, how about yellow? Maybe yellow does not show up very well at all. So I'm going to change that to blue. Oh, yeah, blue. There, now purple. There we go. All right, so I'm thinking something like this would be a good line for this data. Something like that, okay? Fits the trend. It's got a y-intercept of 30. The top speed would be 30 if it had a maximum drop of 0 feet. There are roller coasters like that, the kiddie coasters, right? And then obviously it's looking like the bigger the maximum drop, the faster the roller coaster goes. And that kind of makes sense. Think about the fast roller coasters you've been on or heard about. They have huge drops to them, okay? And that's what builds up the speed. So the question is here, could you use the model to make an accurate prediction? Could we use this line to make a prediction? So if I said the maximum drop was 160 feet, would you feel confident saying that the top speed was about 70? I mean, I kind of would. I wouldn't say it's exactly 70, but I'd say it's probably around 70. Whereas in here, the maximum drop of 100, yeah, it kind of varies a little bit, but I'd feel pretty confident because the points are all pretty close to that line, okay? So here's what I'm going to say. About my confidence level would be high if I made a prediction on the top speed using this model. The points are close to the line. How about that? I want to overthink this, but get some thoughts down. All right, that leads us to our next questions. And I want you to pause the video and answer these two questions. Estimate the correlation coefficient of the top speed of the maximum drop. Is it closest to -1, -0.5, 0, 0.5, or 1? Is the maximum drop of a roller coaster likely to be one of the causes of the top speed of the coaster? So let's think about that. Write down some thoughts, pause the video, and then I'll be back. Okay, so let's see. Here's what I'm going to say. Hopefully you estimated close to 1. It's going to be closest to 1.0, but not exactly 1.0. Okay. So the actual correlation coefficient is R equals 0.89. That's what 0.89 means. So we're not going to get in too much how to calculate what it is, but trust me, I I stole this out of the textbook answers. The correlation coefficient of that data is 0.89. So it's closer to 1 than it is to 0.5, right? So it's a pretty strong correlation coefficient, not hugely strong. You want it over 0.95 to be really, really strong, but there's a decent correlation there. Is the maximum drop of a roller coaster likely to be one of the causes of top speed? Yes, maximum drop has a lot to do with the top speed of a coaster. How's that? And that's pretty obvious, right? And the graph is kind of showing that. All right, let's move on to another situation here. This scatter plot shows the relationship between the top speed and track length. Top speed and track length this time. Okay, so let's put a line on here. You know, it's a little bit tougher to make a line. I still kind of see an upward trend here that the longer the track, the higher the speed of the roller coaster. Longer track, higher speed. Okay, so suppose you drew one liner model for all the data in the graph. I just did that. Could you use the model to make an accurate prediction? So let's put some thoughts down here. Let's put, I would feel less confident making a prediction of top speed if I were given the track length. The points are spread out pretty far from the line, also known as the model, right? If ever I'm going too fast, remember you can just pause. All right. So in fact, I'd like you to pause right now and answer questions 2 and 3, get some thoughts down. Is the correlation coefficient here closest to 1, 0.5, 0, negative 0.5, negative 1? And is the track length of a roller coaster likely to be one of the causes of top speed? Do you think track length is actually causing the speed to go up? Okay, so pause the video, put some thoughts down, and then play it, and I'll give you my thoughts. So there is some correlation here, right? But it's not very strong at all. So I would say this is closest. How about closer to 0.5 than 1.0 or 0.5? And in fact, the book tells me that the correlation coefficient of this data is 0.60. Again, 0.60, closer to 0.5 than it is to 1.0. Okay, so there's something there, but not a lot. And that's what tells me and leads me to this answer for number 3. Is track length of a roller coaster likely to be one of the causes of the top speed of the coaster? Track length seems to have very little effect on the top speed of a coaster. You can have long coasters, long rides that get very fast, and you can have short rides that get very fast. And I'm sure you can think of examples of all of them. Many of you have been to Cedar Point or Six Flags or Disney, things like that. Okay. Computer and calculator data and analysis tools can take data pairs like those plotted above and calculate exact correlation coefficients. And that's where they're getting these 0.6 and the 0.89 of the previous one. Use the tool you have available to find the correlation coefficient for the sample. So we got the sample data. I'm going to show you right now. Okay, so you got to follow along closely. Let's reset our calculator. Second plus 712. Follow along. We pause, rewind if I go too fast. We got to get our data in. Let's go stat, edit. I'm going to put these track lengths in. So let's go 500, 1,000, 1,500. 2,000, 2,500, 3,000, 3,500, 4,000, 4,500, and 5,000. This is obviously just sample data, it's fake. And then let's put these variable or these top speeds in, 5, 20, 45, 50 and 40, 50 and 55, 60 and 85, 65. Again, if I'm going too fast, remember you can pause and rewind. I'm going to turn on my graph. So let's go second, y equals, enter, enter. That turns it on. I need to set up my window. Let's go 0 to 6,000, scaled by maybe 500s for our x values as our track lengths. And let's go 0 to 100 for top speed, scaled by 10s, I guess. And then if we graph that, there's our scatter plot, okay? So think about drawing a line through there and how closely correlated are these values, okay? Now we actually have some scaling on here too, just like we did here. But all right, here's what we do. If you hit the stat button and then you press the right arrow button once, you can calculate linear regression, okay? And that'll give you the slope and y-intercept of the best fitting line. So if I calculate that, it gives me the slope and the y-intercept. It says the slope is 0.011 and that the y-intercept is 19.6. So I can put that in. 0.011x plus, what was it, 19.6, I hope. And there's a line, okay? So the question is, what is the correlation coefficient? Well, I got to do something else. I got to hit second 0. That brings up a catalog of all the functions. And you got to scroll down to the D values, and that's diagnostics on is what we're looking for. And this isn't turned on by default in your calculator, and every time you reset it, it turns it back off. But I want to go diagnostics on, enter, enter. Now it's on. And now let's run that linear regression again. So stat to the right, down to option number 4, enter, and then calculate. And now it gives us that slope, that y-intercept, and it gives us this R value of 0.838. So I'm going to write that in here. So it's R equals 0.84. So again, I went second, catalog, down to the D's. I found diagnostics on, enter, enter. I went stat, calc, linear regression, and calculate. And then it shows me how strong are these two variables related to each other. And in this case, 0.84. Those points are pretty close to that line. Let's keep going. Last one, the scatter plot below shows the relationship between top speed and ride time. The pink dots represent wood frame coasters and the blue dots represent steel frame coasters. I lied, this isn't the right one. Suppose you drew one linear model. Let's do that. I'm saying something like this, maybe. I don't know. It's really tough. I mean, it looks like there's an upward trend, like the longer the ride time, the faster the coaster, but that doesn't even make sense. Like you'd think faster coasters would kind of be over faster, but I don't know. All right. Could you use the model to make an accurate prediction? I would not feel confident at all about a prediction of top speed if I were given the ride time. Points are very spread out from my model. It's just like, if I said the ride time was 2.5 minutes and I went up here, I mean, am I going to say it's 65 when, I mean, I had something as low as like 22 up to, 70 something. I mean, that's a wide range. I'm not feeling it here. The residuals off that line are pretty huge. All right, so my lights went off. Yeah. So estimate the correlation coefficient. I'm going to say closest to 0. Core, how about very close to 0.0? It's not 0.0 exactly. In fact, I've got it right here. It's 0.24. Okay, so it's R equals 0.24. It's not nothing, but I mean, that's almost nothing. So very close to 0.0. Suppose most of the points in a scatter plot cluster near a line with only a few that don't fit the pattern. The points that lie outside a cluster are called outliers. Use the graph above, this one. Find each point, then decide whether the point is an outlier. I don't think this is a good one to talk about outliers because there's not much of a correlation either. How about we go back to a different one? And yeah, like let's go back to the one that had the strongest correlation. Like this one right here. You might say this point right here is an outlier. Let's label that one. So this is on graph B, outlier, because it's so far away from the point or from the line. This one, maybe I'll put a question mark next to it. How about that? Outlier, question mark, because it's kind of far away, but this one too, maybe outlier, question mark. So those 3 points, maybe they're outliers, but you can't have too many outliers and have it still have strong correlation. But this isn't super strong, but it's pretty strong. It's the strongest we've seen. Let's look at another one. This one, I mean, definitely an outlier here, right? Okay, it's really fast for a short track length. Maybe an outlier here. Okay, I'd say those two probably. But on D, I don't really want to make any predictions. I mean, probably this one, I guess, if I had to pick one. It's that same coaster. Was that Top Fuel Dragster, maybe? Top Fuel Dragster's got a super short track, super short ride time, super steep hill, and it's very, very fast. Okay, so that gets that across. Okay, last thing here. The scatter plot below shows the ages of riders related to number of riders. Number of riders to their ages. Okay. I could draw, I mean, we could draw a pretty good linear model here, right? Like something like that. Okay, I'd feel pretty confident about making a prediction off that. Okay. I would feel pretty confident. Making a prediction about the number of riders on this coaster for a given age because the points are very close to the model. So if I said, predict how many riders of age 40 were on this roller coaster, you could probably go to this 40 right here, go up here and go, oh, I think there's about 40 riders that were 40 years old. And I could go to 50 and go, well, I'd say there's only 10 riders that are about 50 years old. I feel pretty confident about that. Okay, is the age likely to be one of the causes? See, this is weird. Yeah, probably. I mean, I'm gonna say yes. Um, Older people are less likely to get on roller coasters. There is a relationship there between age and number of riders because roller coasters are a young person's game. Okay. The correlation coefficient here, it is careful. You got to be careful though, because like correlation does not mean causation. Just because two things are closely correlated doesn't guarantee that one's causing the other. Um, it's kind of tough to word. Even adults have a tough time understanding that. All right. So you pause the video, make a guess. Correlation coefficient? Is it closest to -1, -0.5, 0.5, or 1? All right, the correlation coefficient here is technically, perfectly, -0.94. That is very, very strong negative correlation. So we're going to say this is closer to -1.0 than, yeah, or just close to -1.0. It's not -1.0, but it's close. If I had to choose one of those five. Are there any data points that are outliers? Yeah, I think so. I think we can label an outlier on here, right? That one. There was like a 12-year-old that got on this thing, right? Something like that. So that's probably an outlier right there. All right. Do we hit everything? Is it possible to have a correlation coefficient close to -1 or 1 with only a few outliers? No, not really. We'll say probably not. If there are outliers in a data set, the correlation coefficient would get further away from 1.0 or -1.0. All right, now I think I'm done. Yes, I am. All right. So hopefully you took some good notes. And now you can do your delta math practice, finish up anything that you didn't get to for homework. See ya.